Right. In this video, we're going to be introduced to polynomials in lesson 3.1. And if you notice here, at the top we have this box. We're going to come back to that box after we get done with this first page of notes, because first I want to jump into some of this terminology, and then we'll go back and talk more about some of the properties of a polynomial. So first off, when we talk about a polynomial, we're going to be referencing some different vocabulary words here. As you can see, the first one is just this vocabulary word of term. And that represents a part of a polynomial separated by addition and subtraction. So if we look at this first example down here where we have x squared plus 2x plus 6, each one of these are a term. In fact, that last one, the term would be negative 6. So anything separated by a plus or minus sign is a term. So they don't have to have an x to have it be a term. So anything separated with a plus or minus sign would be a term. So that first example there would have 3 terms. Then the next vocabulary word there is degree. The degree is referring to the largest exponent in the polynomial. Now you got to be careful. It's not always the first one we see. It's always the largest exponent. But in this case here, the largest exponent would be 2. So the degree of that polynomial would be 2. Standard form. We've seen standard form before when we were talking about quadratics. In fact, this first example that we're looking at here that we're already referenced a couple times, that's an example of a quadratic in standard form. So you're starting with the largest exponent down to the smallest exponent. So that's how you know when it's in standard form. But even outside of quadratics, any polynomial can be written in standard form. The leading coefficient. Now, anytime I reference a leading coefficient, I'm going to talk about it as the LC. I'll write down LC. It's just easier to write because I'm lazy and don't want to write down all those letters. But the leading coefficient is a number part of the term with the largest exponent. Okay, that's key. It's not the largest term. It's a term attached to the variable with the largest exponent. So when we look at these next 3 examples and they say how many terms and what is a degree, we're going to include with that what is a leading coefficient, because a leading coefficient is going to have a major, or is going to be a major component to the second half of these notes. So when we look at this first one, we already talked about the number of terms. We said that this one here has 3 terms. And the degree for this one, we already talked about that. The degree is 2 because the largest exponent there is 2. Now the leading coefficient, so that's our leading term. So leading coefficient is a coefficient with that term. And there is no number there, but if there is no number, it's implied that there is 1. So the leading coefficient for that one would be 1. All right, let's look at the next one. So the next one, we could see that there's a total of 1, 2, 3, 4, 5 terms. So this one has 5 terms. The degree, again, is the largest exponent. That's not always the exponent that we see first. This term here has a degree of 4, so that would be the degree of that polynomial would be 4. And that means that the leading term there, that's a positive 2. So the leading coefficient would be just the 2. We don't include the variable, it's just the coefficient, just the number with the variable there. All right, let's look at this last one together. I'll have you do a couple on your own. But this last one, again, there's 1, 2, 3, 4 terms on this one. The degree is the largest exponent, which is 3 for this one. And the leading coefficient, since that's our leading term, our leading coefficient would just be the 7. Now, the only difference between the ones that we just did together and the ones that I'm going to have you do in a minute on your own is that they also ask for you to write it in standard form. So let's look at this first one together, and we'll write that in standard form. So you always start with the term with the largest exponent. So that would be negative 3x to the 4th. So that's my largest term. And then we would go in descending order. So the next one down would be that minus 5x cubed. Now there's no x squared, so we can skip that one. And then we have a plus 2x and then plus 6. So that's how we'd write it in standard form. And now it's easy. When it's in standard form, it's easy to find out what the degree and the leading coefficient would be. And even if it's not in standard form, you can easily find those. So I want you guys to go ahead and find these missing pieces. And then for the next one, find the standard form and the degree, leading coefficient, and number of terms for that one as well. So go ahead and pause this video and hit play when you're ready to check to see if you've done it correctly. Let's see how you did. So for that first one, you should have gotten a degree of 4. And there's 4 terms. And we can see then that the leading term is also negative 3. So again, to illustrate that, the leading term there is -3. So the leading term can be negative, it can be positive. It's not necessarily the biggest number, it's just the number that's attached to the variable with the largest exponent. All right, the last one there, we put that in standard form, so it'd be 2x to the 6th plus x to the 5th minus 3x to the 4th plus 4x cubed minus 8x. That one doesn't have a constant, which is fine. But then we have a degree there would be 6. The leading coefficient would be 2. And if you add those up, there's a total of 5 terms. Now for that space where it says, what do you notice and what do you wonder? If that's something that you wanted to fill out on your own, you can. But let's conclude this side of our notes by going back up to the top here. Let's start with the essential characteristics. Essential characteristics means that these are things that would be in common of any polynomial. So first off, all polynomials will have at least one term. All polynomials have a degree. And all polynomials have the same domain, negative infinity to infinity. And we haven't really talked about what makes a polynomial. This is what makes a polynomial a polynomial. But they're always going to have positive whole number exponents. What is a whole number? A whole number just means that the smallest whole number is 0. And so we would have a whole number starting with 0, then 1, then 2, then 3, and so on. So there's no decimals, no fractions, no square roots. So all of those could be exponents. So as long as you have an exponent that's a whole number, so that even includes, you can't have an exponent that's a variable. And so if you have anything else that looks strange, then it's probably not a polynomial. So before we get into the examples and non-examples, let's look at non-essential characteristics. So these are these are things that would be true of some polynomials, but not necessarily all of them. For example, all polynomials could be written in standard form, but they won't necessarily be written in that way from the beginning. So even though, yes, it is true of some polynomials, they're not all going to be written in standard form, but they could all be could be written in standard form. And not all polynomials have a constant. So a constant, what's a constant? A constant is just a plain old number at the end, like this one. When we had it in standard form, we had a constant there of 6. So some polynomials have a constant, some do not. But the constant is whatever that term is, so that's a term without a variable, that's always going to end up being the y-intercept. We saw that happen last chapter when we were dealing with quadratics. So what are some examples of polynomials? So we've already looked at a bunch, but here's one more. So again, the thing to recognize is that all of the exponents there are positive, and they're all whole numbers. So whole numbers means starting with 0, any number bigger than 0, that's not a decimal or a fraction. So 0, 1, 2, 3, and so on. So the next box, these have some non-examples. So that's important because there's tons of examples we could come up with, and these are some examples of non-examples. So the first one, that would not be a polynomial because you have an exponent that's a fraction, and you can't have exponents that are fractions. The second one, we have an exponent that's a variable, and again, we cannot have exponents that are variables either. And this one, we're going to learn more about roots and what that means for the exponents later. But essentially that means that we would have it raised to the 1/2 power. So we can't have roots of, now if we had the square root of 25, that would simplify to just be 5. And technically that would be a polynomial. But this can't simplify, so to get rid of the root, so that is not a polynomial. All right. Well, on the next page, we're going to talk about how to identify what the end behavior of the graph would look like without having to look at a graph. Now at the top of your notes, you have some space here, so I want you to write down what's at the top of the notes. So pause this video and hit play when you're ready to move on. All right, so what's this top part of the notes that I hand wrote here? What does all this mean? So again, this is to help us identify the end behavior of a graph without having to actually see the actual graph. So this is really, really important. We're always going to start with the right side, and we're going to figure out what's happening on the right side of the graph by looking at the leading coefficient, the LC. So if the leading coefficient is positive, oops, erase that plus, there we go. But if the leading coefficient is positive, the right side of the graph is going to go up. If the leading coefficient is negative, the right side of the graph is going to go down. So again, we always start with the right side of the graph, and it's based on the leading coefficient. If it's positive, the right side goes up. If it's negative, the right side goes down. Once we know what's happening on the right side, then we can figure out what's happening on the left side, because the left side is determined by the degree, which is based on what's happening on the right side. Here's what I mean. So again, the second step, we look at the degree. And if the degree is odd, that means that the left side is going to go in the opposite direction. So it's easy way to remember that. Odd means opposite. If it's even, it's going to go in the same direction. Easy way to remember that is a quadratic. Quadratics, the left and the right side always go in the same direction. Either they both go up or they both go down. So if it's an even degree polynomial, it's going to be similar to a quadratic where the left and right side will both go the same direction. All right, so this box here is basically describing the same thing, except for just done in a little bit different manner. So I like the words that I wrote at the top. That to me makes a lot of sense, but this is helping illustrate the same thing that we just talked about. So the first thing, anytime I'm working with students and they're struggling with these, I always recommend, let me zoom in here. I always recommend drawing these two blanks. So these two blanks represent the left and right side of the graph. We always start with, like I said, the right side of the graph, and the right side is based on the leading coefficient. So if it's positive, the right side of the graph is going to go up. And if it's an odd degree, the odd degree again tells you what's happening on the left side. So odd means opposite. So the left side is going to go in the opposite direction. So it's going to go in the opposite direction on the right side. So if the right side is going up, the left side is going to go down. Now the way this is written down here, this is how we're going to write the end behavior. Okay, so you got to remember that's how we write the end behavior. And that first thing here is identifying the left side of the graph. The left side of the graph, we see from these arrows that it's going down, so we can say it's approaching negative infinity. The right side, that's the next line, as x approaches infinity. That's referring to the right side of the graph. The right side of the graph is going up. So again, it's based on the left and right side of the graph. Let's look at this next box here. So again, you can draw the two blanks. So that's going to help you as you try to figure out what's happening on the left and right side. It's a positive leading coefficient again, so the right side's going to go up. It's an even degree, so that means it's in the same direction on the left side. So the left side will also go up. So that means the left side's going up towards infinity, the right side's also approaching infinity. All right, so let's look at what this box is helping us see. So that, again, we're going to fill in these, I'm going to draw these two lines to represent the left and right side of the graph. And it's a negative leading coefficient, so that means the right side is going to go down. It's an odd degree, so the left side is going to go in the opposite direction. So the left side of the graph is going up towards infinity, the right side of the graph is going down towards negative infinity. Finally, this last box, again, do your two blanks. It's a negative leading coefficient, so the right side's going down. It's an even degree, so the left side's going in the same direction, so both sides are going to approach negative infinity. So these are the four options that we would have with our graphs. But again, I always recommend drawing the two blanks. It just helps you identify what's happening with our end behavior. All right, so we're going to look at this one together. Let me zoom out a little bit here. And so we're going to look at this one together, and then I'm going to have you do the next one on your own. All right, so I always look for the degree of the polynomial. The degree of this one is 6. So 2x to the 6 is our leading term. Whoops. That's our leading term. And that's the only thing I need. All that other stuff, it does impact the graph, like the 1 on the end. That tells us it's going to have a y-intercept of 1. And the other pieces are going to fill in, are going to impact what's going to happen in between the two ends of the graph. But again, all we're working on right now is the end behavior. So we can get the end behavior from just that first term. So it's kind of cool. All that other stuff doesn't matter. All right. So I can see that the leading term is positive. So that means the right side of the graph is going to go up. The degree is even. So that's going to go in the same direction. So it's going to also go up. The left side of the graph is going to approach infinity. The right side of the graph is also going to approach infinity. All right, so I want you guys to do the same thing with this one, and then we'll talk about the graphs at the bottom of your notes and be done for today. All right, so go ahead and pause the video and hit play when you're ready to check to see if you did it correctly. All right, so let's see what you did here. So then, in fact, this is negative. It's a negative leading term, so the right side is going to go down. It's an odd exponent, so left side's going to go in the opposite direction. So the left side of the graph is approaching infinity. The right side of the graph is going towards negative infinity. All right, so this bottom here, this is just illustrating the same thing that we were just talking about. Instead of having the blanks, the two blanks here that we were doing up above, it's showing the left and right side in this way. Now notice what we're doing here with our graphs. When we go to graph something, even though I say the right side of the graph might be going up, or the left side of the graph is going to go up or down, we're never going to go vertically straight up or down. Because think about it, if I had a graph, let's say even a parabola, and I graphed it to look like this, that fails a vertical line test because there it's passing through more than one point. It's never going to go perfectly vertical. If I draw a parabola, it's going to go this way. So it's going to go up and to the right and up and to the left, because now it passes the vertical line test. So what they're illustrating here is when we talk about the graph going up or down, it's always going to go up and to the right or down and to the left, or up and to the right and up and to the left. Okay, so that's the direction the graphs are going to go. It's never going to go down here. It's never going to go down and to the right, and because then we had a graph like this, that fails the vertical line test. Okay, so it's always going to go either up and to the right, down and to the right, up and to the left, or down and to the left. So that's what this is trying to show us here. So it's basically the same thing that we were just talking about it up above, but emphasizing when we talk about it going up or down, it's always going to go never vertically, always at a slight angle. All right, so that's it for today's set of notes for this first part of 3.1, where we're just learning about the basics of polynomials.